problem we are solving today states, let the sum of a sub k x to the k be a power series with radius of convergence r is greater than 0. Show that if the power series converges absolutely at one endpoint of the interval of convergence, then it must converge absolutely at the other endpoint. Justify your answer with the general proof. So first, we start with the most general form of a power series as the sum of a sub k times x minus b to the k. And in our case, b is going to equal 0. The radius of convergence theorem states there is a number r greater than 0 where r is the radius of convergence for which the series converges absolutely if the absolute value of x minus b is less than r. Usually the radius of convergence can be determined by the root test or the ratio test. To find if the endpoints b minus r and b plus r belong to the interval of convergence, substitute x equals b minus r and x equals b plus r into the series and apply the test for convergence of numerical series. Okay, so first we will apply the ratio test to our series. So we take the limit as x approaches infinity of the absolute value of a sub k plus 1 times x to the k plus 1 over a sub k times x to the k. And x to the k plus 1 is going to equal x to the k times x to the 1. So if we substitute that for the numerator and cancel terms, then we get that the limit as k approaches infinity of the absolute value of a sub k plus 1 times x over a sub k. By the ratio test, this value will converge for less than 1. A sub k plus 1 times x is less than a sub k when we multiply a sub k to both sides of the equation. A sub k serves as the radius of convergence and is greater than 0 in this example. If we multiply, or if we determine our interval of convergence, we get negative a sub k is less than a sub k plus 1 times x, which is less than a sub k, or multiplying out the a sub k plus 1, we get the following interval of convergence. To find the interval of convergence with the endpoints, we must test the convergence of the series evaluated at the endpoints of this interval. So for the first endpoint, where x equals negative a sub k over a sub k plus 1, we plug it into the series for x as follows, and b is going to equal 0, so it's just not included. And as we simplify, negative 1 to the k times a sub k to the k plus 1 over a sub k plus 1 to the k. And then if we separate out the bottom, we get for the denominator a sub k to the k times a sub 0 to the k, and cancel terms, we get the sum of a sub k times negative 1 over a sub 0 to the k. And that is in the form of a geometric series. A geometric series states that if the absolute value of r is less than 1, then the series will converge. So here, r is equal to negative 1 over a sub 0, so the absolute value is less than 1, meaning the series converges for r as 1 over a sub 0. The next endpoint, x equals a sub k over a sub k plus 1, plugs into the series where b again equals 0, and we can simplify it all the way out, separate out the denominator and cancel terms, and we get the sum of a sub k times 1 over a sub 0 to the k, which again is in geometric series form. If the absolute value of r is less than 1, which it is, then the series converges. Both endpoints converge for the same value, and that shows that at a radius of convergence greater than 0, if the power series converges absolutely at one endpoint of the interval of convergence, then it must converge absolutely at the other endpoint.